Okay, so we've got the notes for section 10.4, which deals with random variables and probability models. So just some definitions here. So a random variable is a function that assigns a numerical value to each outcome in a sample space according to some random phenomenon. So we denote variables by capital letters such as x, and values they can assume by subscripted lowercase letters x1, x2, xn, so on and so forth. So a probability model is a random variable x together with a function that assigns each possible outcome a probability such that the total of all the probabilities is equal to 1. So in here, we've got an expected value of a random variable. So if x is a random variable with the probability function p of x, the mean of the probability model, mu, is the expected value of x denoted by e of x. The expected value is the sum of the values of x times the corresponding probabilities. So you multiply each outcome by its probability and then add them all up. So if you look at example 1 here, it says a die is loaded, so this favors faces 5 and 6, so it's weighted, it's not fair, shown in the probability model below. Find the expected value for this die, explain what it means. So we take, let's see here, each value times its probability. So 1 times 0.1 plus 2 times 0.1 plus 3 times 0.1 plus 4 times 0.1 plus 5 times 0.2 plus 6 times 0.4. And this will tell us what the should be. So be 4.5. The expected value, or if we rolled it a bunch of times and averaged all of our values, we should get 4.5. Now, if the dice was fair, these would all be 1/6. So it'd be 1 times 1/6, 2 times 1/6, 3 times 1/6, 4 times 1/6, 5 times 1/6, 6 times 1/6, which is actually just the sum of these, 1 plus 2 plus 3 plus 4 plus 5 plus 6, which works out to be 3.5. So if you roll a fair dice a bunch of times, the average should come out to be 3.5, which is halfway between, if you 1 and 6 add up to 7, divide by 2. So there you go. Okay. So example 2, a fundraiser, a student group sells 500 raffle tickets for $2 each. At the drawing, the top prize will be a gift certificate worth $100. Second prize will be a $50 gift certificate. It'll be 5 third prizes, each a $20 gift certificate. There's no question here. Yeah. Whoops. All right, so questions should be, find the probability model. For part A. Part B, expected value. And C, explain. So let's see here. So the probability value, let's see here. So we'll do this. So we'll say x and then p of x. So we got first, you got the second, you got third, and then you have no prize. So these are your outcomes. So we're going to do how much the ticket is profits you. So first prize is actually 98. You made $98. Second prize is you've made 48. Third prize, you've made 18, and no prize is you've lost $2. So the probability here is there's 1 out of 500 winning tickets. Here there is a second prize, so 1 out of 500. Third prize is 3 out of 500. So, 5 third place tickets, so 5 out of 500, which means that's 1, 2, 7. So this would be 493 out of 500. So to find the expected value, we just multiply. So 98 times its probability plus 48 times its probability plus 18 times its probability plus -2 times its probability. And if you work all this out, the expected value is -1.5. Which means on average, you will lose $1.50. So there you go, an average. Okay, example 3, to attract more players on weekends, the golf course offers players at lucky ace, or players a chance, players a chance at a lucky ace discount. When players sign in, manager shuffles the 4 aces and lays them face down on the counter. The player turns over 1 card. If it's the ace of diamonds, the player golfs for free, saving the usually $50 fee. If it's the ace of hearts, the player gets to turn over another card. If the second was the ace of diamonds, the round of golf is half price. If either the first or second card is one of the black aces, the player gets a $10 discount. What is the cost of a round of weekday golf? So let's see here. So you're going to only have 4 cards. So let's see here. So probability of the ace of diamonds is 1/4, because that's one thing that happened, ace of diamonds. If it's the ace of hearts, so probability of diamonds after hearts has been drawn would be, oops, that's probably hearts, then diamond. So drawing the heart would be 1 out of 4, the diamond then would be 1 out of 3, so 1/12. Or you have the probability of, let's see here, if either the first or second card is one of the black aces. So we could draw the heart, then a black card. So that's 1/4 times 2/3, which is 1/6. Or the other option is probably just drawing the black first and ending the game would be 2 out of 4 or 1/2. So here's all our probabilities. Now I need to find the dollar values that you would get for these. So we'll say, since we're talking about what's expected round of cost, whoops, hit the under. So here, for this one, the cost would be 0. Here, the cost is, let's see here, that's half off, so it'd be cost you $25. Here, the cost is $40, and here it's also $40, because you get $10 off in either of these cases. So the expected cost is value times probability plus value times probability plus value times probability plus value times probability. And if you work all this out, the average cost is $28.75 if you do this a bunch of times. All right, so example 4, we roll a fair die 4 times, find the probability that we roll all 3s, no 3s, exactly 2 3s. All right, so all 3s is actually easy. So we're gonna roll it 4 times. So the first times we have a 1 out of 6, then second is 1 out of 6, third is 1 out of 6, fourth is 1 out of 6. So whatever 1 out of 6 to the fourth is. 1 out of 1,296. Which is about, as a decimal, we'll say 0.12377. Okay, so no 3s. Well, that would be 5 out of 6 times 5 out of 6 times 5 out of 6 times 5 out of 6. Because each time I can roll any of the 5 numbers except the 3. Oops, to the fourth. So 5/6 raised to the fourth is 625 out of 1296, which is 0.4823, we'll call it. All right, and the last one, let's see here. Exactly 2 3s. Okay. So 2 3s would be 1/6, 1/6, 5/6, 5/6. So the 3s, the not 3s. So that'd be 25 over 1296. The problem is, though, this is assuming our 3s come in the first 2 die. It could also be first and third, or first and fourth, or second and third, and second and fourth, or third and fourth. So there are 4 dice. We need 2 of them to be well, 3s, sorry. So there's 6 ways to do that. So we actually have to multiply this by 6. This is only the probability of getting one of the possible rolls. So 25 out of, 1296 times 6 is 25 out of 216, which is 0.11574. So this is more likely than that, getting no 3s, but that makes sense because getting no 3s is the highest likelihood. So, all right, moving right along. Binomial probability distributions. Consider a simple event with these probabilities. Each trial has 2 possible outcomes, success or failure. The probability of success on each trial is the same, which means that your odds don't change. Probability of success is P, probability of failure is Q. Note that Q is equal to 1 minus P, because you either succeed or you fail. There's no other option. The trials are independent, which means that one event doesn't affect the other. So let the random variable x be the number of successes in n trials. The probability model for x is called binomial distribution. The probability of getting k successes in the n trial is given by this. So x is successes, I want that many. So it's n choose k, p to the k, n to the n. So p to the k is probability of success. You want k successes. N minus k is the number of failures you have, because you're doing it n times. If k are successes, n minus k is your failure. All right, suppose Michael makes 90% of his free throws. If he shoots 20 free throws, so there's our n. There's our p. And if his chance of making each one is independent of the other shots, what is probably makes all 20? Exactly 18, at least 18. Okay, so all 20 would be, let's see, there are 20 shots. He needs to make all 20 of them. So the probability of success, 0.9 to the 20th. Probability of failure, which would be 0.1 to the 0th. So, which ends up being just the same thing, this as 1. Because there's only, if you have to get all 20 and you're shooting 20, there's only one way to do it. So it's actually ends up being 1 times, or 0.9 to the 20th. Which is probably a very small number. Not too bad. So let's say 12158. So about a 12% chance it makes all 20. Exactly 18. So that would be out of the 20 shots, he needs to make 18. So 0.9 to the 18th, 0.1 squared, because he's going to miss 2 of them. So 18 times 0.9 to the 18th times 0.1 squared. So this is 0.28518. So about a 29% chance that he makes 18. So obviously it should get bigger as you go smaller. At least 18 means he makes 18 or 19 or 20. Now, I've already got all 20. I've already got 18. So if you see an at least or an at most, you have to work out individual probabilities and add them up. So I've already got 20 covered. I've got 18 covered. So at least 18 is 18 plus 19 plus 20. So I need 19s. So this is this, 0.9 to the 19th, 0.1 to the 1st. So this is what I'm missing. So this is 0.27017. So this plus the likelihood of making 20 plus the likelihood of making, 0.18. So let's see here, 0.27017 plus 0.12158 plus 0.28518. So 0.67693. So it's about a 68% chance of making at least 18 or 19 or 20. He has a 29% chance of making exactly 18, 12% chance of making all 20, even with his 90% shooting. Okay, fair coin is flipped 5 times. What is the expected value of the heads? Okay, so let's see here. So let's write a little table. So X will be the number of heads. So you could get none, you could get 1, you could get 2, you could get 3, you could get 4, you could get 5. The probabilities, we're going to have to use our formula for. So this would be 5C0, 1/2. Now this one's just going to always going to be 1/2 to the 5th, because success and failure are the same, so it doesn't actually matter. So let's look at here. So 5C0 times 0.5 to the 5th. 1 out of 32. So this one's going to be, so 5C1 times 0.5 to the 5th. So there's 5 out of 32. So this one's going to be 10. This one is also 10. This one is 5 again, so it should go back down. They should mirror each other. So there's your probabilities. So the expected value is value times probability plus value times probability plus value times probability, so on and so forth. Then plus 5 out of 132. So all of this comes out to be 2.5, which you might have been able to guess. Because if it comes up heads half the time, you should get about half. Obviously, you can't get fractional heads, so this is just kind of mathy. Okay, expected value for a binomial. If the binomial random variable x counts the number of successes in n independent trials with probability of success p, then the expected value is just n times p. So in the previous example, 5 flips, probability of success 1/2. Expected value is 5 times 1/2 or 0.5. Okay, chimpanzee is shown 100 questions from a multiple choice test in organic chemistry. As each question appears on the screen, the chimp randomly presses 1 to 5 buttons, A, B, C, D, or E, to indicate its answer. What is the chimp's expected score? So, n, number of events. So the expected score is equal to NP. Well, n is 100 questions. The probability of getting the question right is 1 out of 5. So their expected score is 20. Okay, standard deviation is given by this formula, square root of NPQ, where Q is the failure rate. If many chimpanzees take the 100 question multiple choice test in organic chemistry, what's the standard deviation? Well, sigma square root NPQ. So that's the square root of 100 times 1/5 times 4/5, because if you write 1/5 at the time, you're wrong 4/5 at the time. So 100 times 1/5 times 4/5 is 16. So the standard deviation is 4. Okay, normal model. We have this thing called the z-score. A z-score measures the distance from the mean in standard deviation units. For random variable x has mean mu, standard deviation sigma. For a given value of x, z is equal to x minus mu over sigma. So you're counting the standard deviation while you divide by it. Okay, so number 9 here. According to the National Health and Nutritional Examination Survey, the height of adult American men can be described by a normal model with mean of, so there's our mu, 69.2, standard deviation of 2.8. What is the probability that a randomly selected adult male is in between these two values? So, let's see here. So, let's see. So we need a z-score for both of the numbers. So the z-score for 65, and the z-score for 70. So the z-score for 65 is your value minus your average divided by your standard deviation. Over here, it's going to be value 70 minus average 69.2 divided by the standard deviation. So 65 minus 69.2 divided by 2.8 is a z-score of negative 1.5. For 70, 70 minus 69.2 divided by 2.8, this comes out to be a z-score of 0.286. Okay. Now there are tables that give you this that you can use to calculate these. I didn't pull them up, but you'll have them in class, and we'll talk about how to use them. But you find that what you do is you find the probability, if you're on your table, you find your z-scores, and you can look up the probability that your value is less than them. So since this is the bigger value, you take whatever probability from this minus the probability of this. So the probability that you are between 65 and 70 actually comes out to be about 0.547. So over 6 feet tall, well, this is 72 inches. So we need our z-score for 72. So that's going to be 72 minus 69.5 divided by 2.8. So 72 minus 69.5 divided by 2.8. So this is 0.893. So we'd look up that z-score in our table. Now, since we went over, our table gives us values less than, so we would take 1 minus whatever this probability came out to be. So this actually comes out to be, no, not 16.5, 69.2. That's going to change my answer. 72 minus 69.2. Can't get it. 72 minus 69.2 divided by 2.8. This is actually 1. So if you look at our table, we find our z-score 1, look at our percent less than it, but since we want more than, we do 1 minus that. So this comes out to be the probability that you are taller than 72 inches. Comes out to be 0.159. Shorter than 5'6", so this is 66 inches. So the z-score for 66 inches is 66 minus 69.2 divided by 2.8, which if I calculate this out, negative 1.14. So we'd find 1.14 in our table and just look up the probability because it's less than, so shorter than. So the probability that you are less than 66 inches is going to be about 0.127. Okay, 10 here. Heights of adult American men can be described by normal model, blah, blah. The shortest 20% of men are less than 1 height. So we actually need to work backwards. We know our probability, so we need to look up a z-score from that thing. So we'd find the probability in our table and find the z-score that corresponds to it. So a probability is it 20%? So 0.2. So the z-score that goes with that height is going to be negative 0.842. And then we can actually solve backwards. So we know our z-score, so negative 0.842 is equal to what height minus the average divided by the standard deviation. So negative 0.842 times 2.8, then add the 69.2. So this height is 66.8 inches. So 20% of men are shorter than 6 foot or 5'7"-ish. How tall are the 1%? Tallest 1%. So we'd find the z-score that has 99% less than it. So I'm looking for the 99th percentile, essentially. So if my probability of x is greater than h is 0.1, our table is set up to find less than, so that's going to be, equals 0.99, which corresponds to a z-score of 2.33. So 2.33 equals what height minus 6.92 divided by 2.8. So 2.33 times 2.8 plus 69.2. This one goes there. So this comes out to be a height of 75.7 inches. So that would be 6'4"-ish if you converted it to feet. All right, and then we got the normal approximation for binomial distributions. So success failure rule, if we expect at least 10 successes and 10 failures, with the binomial distribution, the number of successes can be approximated by a normal model, blah, blah, blah. So example 7 and 8, we imagine chimpanzees choosing 1 of 5 answers, a random 100 question multiple choice test. How high a score might a lucky chimpanzee be able to get? So we can use this to approximate the average and the standard deviation. So the average is NP, which was 20. The standard deviation was the square root of NPQ, so that was, I believe, 4. So it depends on how you defined lucky. So we'll say So, 68% of them will be between, that's a bad example. So let's still talk about 95%. So 95% is within 2 standard deviations, so 20 plus or minus 2 times 4. So that's somewhere between 28 and, what's it going to be, 12. So if we go up another standard deviation, so 20 plus or minus, so this is going to be 97%. I don't remember what the percentage is for the next standard deviation, but scoring more than 28 is probably pretty lucky. And if you go up one more standard deviation, 97% maybe, this gives you somewhere between 32. So scoring above 32 would definitely be very lucky. Or being helped. And that's even though out of 100 questions, 32 is still, they might know something after all. But that is the end of the section.